Hi everyone, this is part 2 Calculus 1 exam questions. In this part I have prepared 5 curve sketching problems for your midterm exam or final exam. The first 2 questions are multiple choice questions. The other 3 questions are very famous, very known exam questions. So let's start from the first 3 questions. The graph of f is given on the left hand side of the page, and the question is requested to find which one is not correct. A. The curve has 2 local extremum points. When you look at the graph, you see that you have one local minimum, one local maximum point. So this is correct. B. The curve does not has a horizontal asymptote. The curve has an oblique asymptote. Here, this is the oblique asymptote. The curve has a vertical asymptote, which is x equals 1. Okay. But the curve does not has a horizontal asymptote. This is correct. When x tends to 1 from right, limit of f is infinity. If you approach to the point 1 from right, you see that the function tends to infinity. This is correct. D. Limit of f minus this function is equal to 0 when x tends to infinity. Let's try to understand what is this function. Y equals x plus 6 over 2. If you look at these 2 points, minus 6, 0, and here you have 0, 3, and you see that this line passes through these 2 points, minus 6, 0 and 0, 3. So using these 2 points, you see that this is actually the line x plus 6 over 2. So this is our oblique asymptote. By definition of oblique asymptote, when x tends to infinity, the function tends to that oblique asymptote. So this is correct. E, finally, limit of f is infinity when you approach to the point 1 from left. Let's approach to the point 1 from left. What do we see? We see that the function tends to minus infinity, not infinity. This is not correct. E is a true, correct choice. Question 2. Which one is not correct? A. F, the graph of f is concave down from minus infinity to 1. Let's remember the definition of concave up and down. If you have something like this, it means the function is concave up there. If you have something like this, the function is concave down there, right? From minus infinity to 1, this is the point 1. From minus infinity to the point 1, you have something like this. This is why the function is concave down. This is correct. B. From 1 to infinity, you have something like this. This is why the function is concave up. This is correct. C. F prime is decreasing for that interval. What's the meaning of f prime decreases? If f prime decreases, derivative of f prime must be negative, right? So the sign of f double prime must be negative. So what does it mean? If the sign of f double prime is negative, in this case, the function is concave down there. So from minus infinity to 0, yes, the function is concave down. We found that. This is correct. D. F prime is increasing. What's the meaning of f prime is increasing? If f prime increases, the sign of derivative of f prime must be positive. So the sign of f double prime must be positive on the given interval. From 1 to infinity is the sign of f double prime positive. What's the meaning of this? In this is from 1 to infinity is the function concave up. Yes, from 1 to infinity, 1 to 2 actually, the function is concave up. But it is not the only interval. It is not the only interval which the function is concave up. The function is concave up from 1 to infinity, not from 1 to 2. This is why that one is not correct. Let's look at the last choice, E. F is increasing for this interval. Let's look at the graph from 2 to infinity. From 2 to infinity, yes, the function increases. This is why that one is also correct. Let's look at other questions. A rational function ln x over x is given in question 3, and the domain and x must be positive since ln function, we have ln function in the function f. Let's read the questions. The first one, find the critical points of f, and the second one, classify them. In order to find critical points, we need to find f prime using the derivative rule. For rational function, derivative of ln, derivative of numerator times denominator, 1 over x times x, minus derivative of denominator times numerator, minus ln x over x square. Okay, so you have 1 minus ln x over x square. For which values of x, f prime undefined, when x is 0, f prime undefined. Okay, so is it the critical point? No, it is not the critical point. It is not the critical point since it is not in the domain of the function. What else? Do we have any point that makes f prime 0? If 1 minus ln x is equal to 0, in this case f prime becomes 0. So we have this situation. If x is equal to e, right? If x is equal to e, ln e becomes 1. 1 minus 1 is equal to 0. So this is the only critical point of the given rational function. Let me write down e here. I want to prepare a related table to understand the extrema of the functions and the intervals of the functions where it increases and decreases. So we need to find the sign of f prime. When x is smaller than e, you see that f prime is positive. This is f prime. When e is, of course, x starts from 0, not minus infinity, by domain of the function. If x is in between 0 and e, f prime is positive. If x is greater than e, in this case, for instance, if x is e square, for instance, you have a negative number. So the sign of f prime becomes negative. If f prime is positive, the function increases. In this case, this is the function decreases when f prime is negative. So the only maximum point, the only local maximum point is the point x equals e. Local maximum point. We do not have any local minimum point. And the third question, find the absolute extrema of the function on the given interval, 1 e square. In order to find absolute extrema of the function, we need to find values of f at the critical points and at the given endpoints. So we need to check what is f of e, what is f of, let's check the endpoints, f of 1 and f of e square. F of 1 and f of e square. Okay. F of e, look at the function again. We have ln x over x. So you have ln e over e, which is 1 over e. For 1, you have ln 1 over 1, which is 0. For e square, you have ln e square over e square, which is 1 over, 2 over, right? 2 over e square. 2 over e square. Which one is biggest? As you see, 1 over e is greater than 2 over e squared, and this is greater than 0. So what is absolute maximum point? Absolute maximum point is the point e 1 over e. What is absolute minimum point? Is the point 1, 0. Okay? This is all for the question 3. This is the question 4. Consider the function which is given by this expression. As you see, the function is not directly given, and you have this expression. If you look at left hand side of the equality, you see that this is actually definition of derivative of inverse function. So this is the formula of the definition of derivative of g, right? So this is that one actually. So this is equal to f of x in this case. Let me substitute f of x. Let me take the parentheses of x to the power 4 here. You have x minus 5. In this question, we need to find domain, intercepts, and asymptotes of the given function. We need to find increasing, decreasing intervals and extrema, and finally inflection points, and decide the concavity of the function. So let's start from the domain of the function. Since you have a polynomial, the domain is everywhere, all real line. What about the intercepts? When y is 0, x is 0. So 0, 0 is the one of the intersection point. If x is 5, then y is 0. So 5, 0 is another intercept of the function. What about vertical, horizontal, and oblique asymptotes? Since you have a polynomial, you cannot have vertical, horizontal, and oblique asymptotes for this function actually. For instance, when x tends to infinity, this function tends to infinity, so you cannot have vertical or horizontal asymptote. You don't have any point that makes the function undefined, so we skip this part. What about the critical points? In order to find the critical points of the function, you need to find f prime first, right? Let me write down f prime. This is very easy to find f prime. 5x to the power 4 minus 20x cubed. If you substitute this expression, take the parentheses of x cubed, 5x cubed actually, you have x minus 4, right? X minus 4. So we have 2 points that make f prime 0. Let me write down these 2 points. X equals 0 and x equals 4 makes f prime 0. This is why, and they are in the domain of the function. This is why they are the critical points of the function. Let's also write f double prime here. We need to find f double prime to find inflection points. I shortly write f double prime. Take the parentheses of 20x squared. You have x minus 3. If you make it equal to 0, then you see that x equals 0 and x equals 3 are the inflection points of this function, since, again, these 2 points are in the domain of the function. Now we are ready to prepare the given table. I need to write inflection points and critical points here. The smallest one is 0. You have 0 here, 3 and 4. We need to find the sign of f prime and f double prime to find the behavior of the graph. From minus infinity to 0 to the point 0, if you look at the f prime, you see that the sign of f prime is positive. From 0 to 3, the sign is negative. From 3 to 4, the sign is negative. And when x is greater than 4, in this expression, you see that the sign is positive, plus. What about the sign of f double prime? This is the definition of f double prime. From minus infinity to 0, for all negative numbers, f prime is negative, f double prime is negative. From 0 to 3, it is still negative. From 3 to infinity, the sign of f double prime is positive. So what about the concavity of the function? What can we say about the concavity? Since f prime, let me first talk about increasing decreasing intervals. Since f prime is positive, the function increases. Since f prime is negative, the function decreases here. And finally, the function increases. Okay, what about the concavity of the function? Since f double prime is negative here and f prime increases, you have something like this. Okay, and it is concave down, as you see, concave down, concave up, concave up. Since the function decreases and it is concave down, decreases, and down, you have something like this. The function decreases and concave up, decreases and concave up, and finally the function is concave up and it is increasing. You have something like this, okay, on the given interval from 4 to infinity. What about the extrema of the function? As you see, the point 0 is the maximum point. The point 4 is the minimum point, right? So f of 0 is 0. This is why 0, 0 is a local maximum point. Okay. F of 4 is equal to minus 256. So this is why this point is the local minimum for minus 256, local minimum point. And what about the inflection point here? Inflection point. Let me write down this. For 3, f of 3, you have minus 162, and this is the inflection point. Also, this point is the other inflection point. Okay? So this is done for this question. This is the final question of this part. Sketch the graph of f of the given rational function. Let me first start from the domain of the function. We have 2 points that make denominator 0. So they make f undefined. So this is the domain of the function. The function is defined except the points minus 4 and 4. What about vertical asymptotes? As you see, the function is undefined at the points minus 4 and 4. So when x tends to 4 from right and left, we must examine the behavior of the limit of the function. So when you look at the limit, you see that numerator is always positive when x tends to minus 4 or 4. So the sign of numerator is always positive. Okay. What about the sign of denominator? So all these results are infinity, since all these points minus 4 and 4 make denominator 0. So this limit is infinity. We should decide the sign of the limit, the sign of infinity. Is it positive infinity or negative infinity? When x tends to the point minus 4 from left, you see that denominator becomes plus. So this is plus infinity. When you approach to the point minus 4 from right, you see that you have minus infinity, not plus infinity, since you have minus here. When you approach to the point 4 from left, you see that denominator is negative. If you approach from left, you have something smaller than 16. This is why you have negative here. Yeah, right. When you approach from right to the point 4, you have something greater than 16. This is why the sign of denominator is also positive, and you have plus infinity. What can we say about this vertical asymptotes? We can say that x equals minus 4 and x equals 4 are two-sided vertical asymptotes. What about horizontal asymptote? When x tends to infinity, this limit is equal to 2. So it means y equals 2 is the horizontal asymptote of this function. What about the oblique asymptote? Do we have an oblique asymptote? No, we don't have oblique asymptote, since the order of numerator is equal to the order of denominator. This is why we cannot have an oblique asymptote. So in order to continue to prepare the table, we need to find f prime and f double prime to find the critical points of the function. What is f prime? If you calculate, you see that you have minus 48x over x square minus 16 square, and f double prime is equal to, take the parentheses of 46, you have 16 plus 3x square over x square minus 16 cube. Okay. So what is the critical point of this function? As you see, the points minus 4 and 4 makes denominator 0, so makes f prime undefined. So are they the critical points? No, they cannot be the critical points, since they are not in the domain of the function. So what are the critical points? We only have one point that makes f prime 0. This point is x equals 0. So x equals 0 is the only critical point of this function. What about inflection points? Do we have an inflection point? No, we don't have an inflection point. We have 2 points that make f double prime undefined, minus 4 and 4 again, but they are not in the domain of the function. This is why they cannot be inflection points. So the next question is, do we have any points that make f double prime 0? No, it's not possible to make f double prime 0, since you have x square here and you have plus here. So it's not possible to make numerator of f double prime 0. So we don't have any inflection point. No inflection point. Okay. I actually skipped the part of intercepts for this question. When x is 0, f is 1 over 2, as you see. When x is 0, sorry, f is 1 over 2. So 0, 1 over 2 is one of the intercept of the function. What else? If f is 0, okay, if f is 0, then x is plus minus 2. So we have 3 intercepts, 3 intersection points of for this function. So let's prepare the table to find increasing, decreasing intervals and concavity of the function. In general, I only write the critical points and sometimes inflection points to prepare a table. But now I also write minus 4 and 4, which are the vertical asymptotes of the function, to this table to see the behavior of the function. So we need to find the sign of f prime on these intervals. From minus infinity to the point minus 4, What is the sign of f prime? F prime is given here. Denominator is always positive. From minus infinity to minus 4, as you see, numerator is also positive. So the sign is positive. From minus 4 to 0, you still have the same thing, right? The sign is positive. And from 0 to infinity, numerator becomes negative. This is why f prime becomes negative. Okay. What about the sign of f double prime? As you see, numerator is always positive for each values of x, no problem. So the sign of denominator, we should look at the sign of denominator. This is important. When x is from infinity to minus 4, the sign is positive. Actually, what do we see? We see that, yes, this is positive. From minus 4 to 0, the sign of f double prime is negative. From 0 to 4, the sign is still negative. Okay, look at this, the given expression above. And from 4 to infinity, the sign of f double prime is positive. Okay, so let's go back to the table, the first row. Since f prime is positive, the function increases and the function decreases here. What is the local extrema? The only local extrema, the local maximum, is the point 0 here. What about the concavity of the function? Since the function increases and the function is concave up, concave down, let me write down this also. The function is concave up here and increases. This is why we have something like this. The function increases and concave down, we have something like this. The function is concave down and decreases, something like this. And finally, the function decreases and concave up. Decreases but concave up. We have something like this. I think now we are ready to prepare to sketch the graph using all this information. This is the graph of the function. This is x equals minus 4 vertical asymptote, and the other asymptote x equals 4. This is y equals 2. Using the information given above, we see that we have 3 intercepts. One of them is minus 2, 0, right? Minus 2, 0. Let's say this is minus 2, 0. And the other one is 2, 0. And the other one is 0, 1 over 2. Let's say this is 0, 1 over 2. And the function must passes through these points, and using the concavity information, using the increasing decreasing interval information, we see that we have something like this for this piece of the graph. Let's continue. From minus infinity to minus 4, using concavity information, we have something like this. From 4 to infinity, again, using the information given in the table, we have something like this. This is the graph of the function. This is all for the time being.